Okay, welcome back Physics 30s to our next lesson in Chapter 3. This is 3.5, and today we're going to be talking about Lenz's Law. So remember in the previous lesson that we looked at a diagram like this and said that you can induce an electric current or create electricity by moving a conductor in a magnetic field. Because the conductor has electrons in it, and if these electrons are going to be moving perpendicular to this magnetic field in the background, so I'm going to push it perpendicular like this, then I can use my third hand rule and point my fingers in the direction of the field lines into the page, my thumb in the motion of the electrons, and there should be a force down. So field lines into the page, thumb in the direction that the electrons are moving, and then the force should be downwards in the direction of the palm, so the electrons are going to flow in that direction. If we move it like that and we get electron flow, we should be able to get electricity to power a light bulb. As we can see, the light bulb turns on. Now that worked really well when the motion was perpendicular to the magnetic field lines, and then the conductor was running perpendicular to the motion of the electrons. So the perpendicular force caused it to flow down and create electricity. But today we're going to look at a solenoid. We're going to look at a demonstration with this magnet over here and this solenoid. There's a couple other solenoids here, but we're going to look at the one with the most coils so we can look at the most current. Now this measurement over here is going to be measuring the voltage that is going to be occurring in this solenoid. Now it may be kind of hard to see the wires, so let's just simplify it to looking like this. We have the two ends of the wires hooked up here, which are going to measure the current in between there, and then we have these loops wrapped around the solenoid. And in this demonstration, we're going to take this magnet, and the left end of that is the north end of the magnet, and we're going to move it into the solenoid. This is similar to that first example where we had our field lines and we had a conductor and we moved the conductor in the magnetic field. It doesn't actually matter if you move the conductor or move the magnetic field. As long as they're moving relative to each other, we should still get the same effect. So this would be the same as moving the solenoid closer to the magnet, but it's just easier to move the magnet, so that's what we're going to do. Now as this magnet moves into the solenoid, we might use our third hand rule to try and figure out the current. So if I'm looking at the electrons here in the wire, I'm going to put my thumb pointing in the direction that they're going to be moving. Now again, you could move the solenoid this direction, or we could move the magnet closer. Either way, they're coming together like this, so I'm going to be pointing in this direction. So I'm going to put that with a yellow arrow showing the direction of the electrons relative to the magnet. And now I'm going to put the field lines of the magnet. The field lines come out of north with this green arrow. Now you can see that with my hand I run into a problem. I'm pointing in the direction of the yellow arrow and I need to put my fingers in the direction of the green, but I can't get my fingers to be in the opposite direction of my thumb. So this becomes a problem for the third hand rule. And the third hand rule was applying to electrons going through wires. So if I slide this up and say that this electron was in a wire that was in the same plane as the magnetic field, this actually leads us to a good conclusion that there isn't going to be any force, nothing that we can do with our hand here, because when the electron wire is in the same plane as the magnetic field lines, we're not going to get a force. We needed the electron to be going perpendicular to the field lines. So in a wire, this electron would not feel a force and we wouldn't get a current. But this is not just looking at a straight wire. This is looking at a solenoid, and the wires are wrapped in this direction. And this does show vertical lines that are going to be crossing the magnetic field lines. So this means that we should get an electric current. And so when we try it out, we can see that we do get an electric current.
And I'm going to take a magnet and I'm going to push it into this solenoid. Let's observe what happens on this ammeter. Notice that I make a current as I plunge it in. And while it's in there, while there's no motion, while I'm not cutting magnetic field lines, the current is zero. But if the magnet is moving, or the wires are moving with respect to the magnet, it doesn't matter, then a current is formed.
So this is really good. Again, we can make electricity by moving a magnet relative to a coil of wire. We can make electricity, that's a good thing. But now how do we determine what direction the current's going to go? Well, there's really only two options. When the magnet goes down, we could either have the current going in this direction, or or we could have it going in this direction. There are only two choices. But let's remember that when that magnet goes down, if there's going to be electrons spinning around, we had a left-hand rule, the second left-hand rule, for a solenoid that said this will create a magnetic field in the solenoid. We would wrap our fingers in the direction of the electrons and we would point in the direction of north. So this is going to make the solenoid either a magnet like this, or if it flows in the other direction, a magnet like this. Now you might be thinking, okay, it could spin one way or spin the other. Who cares? The universe cares. Huh? Yeah, the universe cares about this.
This is actually pretty important to me.
Let me show you why. Let's consider that the magnet is held up to this certain height, and then we're going to drop the magnet onto the ground. The magnet began with potential energy and then ended up with kinetic energy. Based off the first law of thermodynamics, if it started with 100 joules of energy, it should finish with 100 joules of energy. Again, not worrying about any air resistance. Okay, so let's consider that if the magnet moves down like this, and that induces a current going in this direction. And let's say that that makes a magnet that looks like this. This makes it so the solenoid has a south end at the top and a north end on the bottom. That south end on the top is going to attract the north end that was falling downwards. So we're going to get an attractive force down to this top magnet. Okay, so what would that do to our energy? Again, we start with potential energy. Let's say, again, that was 100 joules. Now let's look what happens to our kinetic. If it's pulled down, it's going to be pulled down by that force of the magnet. So it's not just going to be going at 100 joules, but it has extra energy from that force pulling down. So that might say have something like 110 joules. Another thing we've done as well is when that magnet moved, it created electrical current flowing through there. So now we have another form of energy in the form of electrical energy. And let's just say that's an extra 10 joules. So now we've gone from 100 joules of energy at the start to 120 joules total at the end. We've created energy. And then the universe comes in and says that that is not allowed. You cannot create energy. Energy cannot be created or destroyed. So if that's not possible, this situation must be possible, where it spins in the opposite direction and it makes a magnet flipped, where it's got north at the top and south at the bottom. Let's take a look at energy now. Again, it starts with potential energy, so let's say 100 joules, and then as it falls down, now the north is moving towards the north being induced by the movement of that magnet. So the solenoid has a north on the top. So that's going to be pushing upwards against the fall of the magnet. So now when we look at the kinetic energy, it's been slowed down by that upwards force. So now maybe we have something like 90 joules of kinetic energy. Now, it's not that we got rid of energy. Remember, just as much as energy can be created, it can't be destroyed. So where did that energy go? It went into the electrical energy flowing through the solenoid. We would have an extra 10 joules there. So whatever we lost in kinetic has become electric, and the universe is happy.
Oh, thank you for following my rules. I really appreciate it.
The same would apply to lifting a magnet up. Let's say this is a much lighter magnet and you only have to do 10 joules to lift this one up. If there's no coil present, we lift it up, we do 10 joules of work, and we should get 10 joules of potential energy at the end. Now with the solenoid, let's imagine lifting it back up out of that solenoid. If when we lift it up, it flows in the same direction as it fell, in this direction here, we would get the north on the top and the south on the bottom like we did when it fell. But now that we're lifting it back up, we run into a problem with energy. This north and this south are going to repel. So there's going to be a force upwards. So before I had to put in 10 joules of work, but now if the magnet is also lifting it up, I don't have to do as much work. Maybe I only have to do 8 joules of work because I'm getting help from the solenoid. And then at that height though, that height's the same height as we were at before, so it still has 10 joules of energy. I did 8 joules of work, somehow got 10. And let's also not forget that there's electrical energy being generated in the solenoid. Maybe say another 2 joules of energy. So we run into the problem again where we're making energy from nowhere. And so once again, the universe says that is not allowed. So that means when I move the magnet in the opposite direction or pull it out of the solenoid, the current has to go in the opposite direction. Now the north and the south are going to attract. So there's going to be a force downwards on that magnet. So now to get that 10 joules of potential energy, I had to lift against gravity and against that force that the solenoid was pulling down with. So maybe I had to do 12 joules of work to lift it. Okay, well, where did that extra 2 go? It went into the electrical energy in the solenoid, which would be in this case 2 joules with the electric energy. So no matter what direction you move the magnet, it's going to induce a current in the solenoid that is going to oppose that motion. It can't increase the motion that is already occurring. It has to oppose it so that energy is conserved. This is Lenz's law. It says that induced current from moving a magnet will flow in a direction to oppose motion or oppose an applied force. And this is due to the conservation of energy.
I push the north in, the electrons are going to have to chase around in such a direction to create a north that opposes you pushing the magnet in. So now I can feel I'm pushing against something. I'm pushing against the new induced magnetic field, and it's that force which is causing the electrons to flow. So which way would the electrons flow as I push this north into the magnet? Okay, let's imagine that this deflection was because of that electron flow. Now the magnet's inside and nothing's happening. But as I move the magnet again, I'm going to try and draw that north out. If this end is still north, it'll help me. Again, that would break the law of conservation of energy. Instead, what must have to happen is this will become a south to oppose me pulling the north out. And we saw that on our ammeter. They flowed in opposite direction. Let's watch again. In, out. The electrons chase around this coil in opposite directions because Lenz's law tells me which way the electrons must flow in that copper coil.
So that's it for this video. You'll see in the practice questions there's some other scenarios and diagrams that you'll have to solve for current and force, but again, they're all the application of conservation of energy and Lenz's law. So I hope this video has helped you to understand those concepts. Thank you so much for watching, and I will see you in the next video.